like sing and ching, or you know what I'm saying? No, like.
What?
Do you have Chinese words that rhyme? You know, like row and o, or like ring and sing.
Oh, yeah.
Yeah. You have like when you do poetry in Chinese.
Yeah.
In poetry.
I don't know.
So yes or no?
What yes or no? Yes.
Yeah. Okay. Anyways, row
Over row F equals VF over VO.
Yeah.
Equals
Equals what? Another equal?
FB
FG over
or FB over FB.
Check your equation sheet, Sue.
FG.
Oh.
Oh.
I don't care about that. I can get it myself.
Oh. I don't care about that. I can get it. All right.
I will get a Sue teach on Friday.
Yeah.
Oh.
For us.
Yeah. Sue knows. All right. Now let's discuss. What does the left what does the left ratio say? AJ.
Momentum of the object. Wait,
That's probably a pretty big issue.
not momentum. Let's see. I just forgot. Density of the object or the density of the fluid.
Fluid. Okay. So the ratio of the density of the object to the density of the fluid. Let's talk about this clip. Okay? In water. Which one's bigger, Mick? Top or bottom?
Top.
Good. Volume of the fluid, volume of the object. Specifically, what are we talking about? The displaced fluid. Okay? Which one's bigger? They're equal to one another.
So it's gonna be one all the time.
So it's going to be one all the time?
Unless it's floating object.
Unless it's floating. See, and that's where I don't understand, Sue. You know, if this is 1, well, that means that this has to be 1. You know?
Yeah, if the thing is in the water,
Yeah.
and stay in somehow that in the water, they are the same density.
Yeah. This has to do, remember, with objects that are.
I know.
Go ahead.
Submerged.
Submerged, not objects that are sitting on the bottom.
Well, that is submerged.
Well, this does not
The
apply.
volume part does. The density part does not.
Right. Well,
They have to be.
well, yeah. I'm saying this does not apply, and you said this part does, that part does. Well, this is part of that. I mean, if this is a full equation, you know.
But it's also for the floating things.
It is for the floating things. Because if you think about this, with a floating thing, what does not have to be true about this, Mick? This. Prior to this, we said that this was always going to be 1. When it's floating, it's not. Which is greater, the top or the bottom?
When it's floating.
When it's floating, Mick.
Bottom.
Why?
Because the water that come out is less.
Yeah, the water, we only displaced half of the object, if you will, roughly half of the object's total volume, you know. What about the far right one? What does that talk about, Mick? FG, FB, what are they?
Force of gravity.
Okay.
Force of buoyant.
Buoyancy, yeah.
Buoyant force. Okay. So here's a question that I'm going to pose for you. It's a little bit simpler than the homework. We're all five going to do this. Go ahead. Figure it out. How much do you weigh in water? And report. The things that you might need to, what is it, 2.24
Pounds per kilogram.
pound.
2.242, I think.
What?
No, I was talking about Newton's 4.8.
Oh. 4 point. I forget.
Flip back.
Is it 4.844?
Something like
There's two
that.
fours, I know that.
2.8.
Not just 4.8. Exactly. I got to hold on. Count kilograms here. One, no. 4.448. 1 pound is
4.448.
I found it first.
Go ahead, guys.
So it's pounds or
I'll do mine on the board.
I'll do mine on the board too.
If we already know our kilograms, we just multiply that times 2.
Yeah, that's fine. What's 210 times 4.448?
934.08.
wait,
So,
how do you get the buoyant force?
I don't know.
You don't know your buoyant.
We need either our density or our volume.
Yeah, I know.
I don't know what the density is of a given body. I was looking at the chart here, but it's not there, and then my page got turned somehow.
Let me think here.
Well, it also depends. I mean, are you lunch full there or
Yeah, and also, are you a female or male? Because males are more dense than females. Not up here. Female, we're in the end, we're probably as dense as each other because males are more dense here and female, no. Funny. That was a joke.
So are we assuming that we're not floating?
Yes, we're not floating. How do we calculate buoyant force?
But you can stay in the water.
I can.
No, I mean, not.
You might not be able to, I can. I
I mean,
can stay in the water for
Oh,
hours.
no, I mean not standing there. Just stay in some height.
Yeah, you're submerged.
Yeah. You probably will keep moving.
we're finding buoyant force, right? Is that what we're finding?
Yeah.
Okay. My buoyant force.
No, we're not finding buoyant force. You're finding your weight.
Okay.
Your weight in water.
There's my weight in water.
But we have to know.
If I'm floating.
You're not floating.
What am I doing then?
You're submerged.
Putting down on the ground?
Right.
Okay, then here's my weight.
That's impossible. You're submerged in the
That's
water.
why I asked if you're floating or not, though, 'cause otherwise.
It doesn't matter. As long as I'm not on the bottom, the water's supporting my full weight, whether I'm on top of it or whether I'm within it.
No, but there's no force if you are at the bottom.
Mm-mm.
If I'm at the bottom, then my density is greater than
No. You're missing what I'm saying. If I have to carry your butt around in the water, it's not going to be weightless.
But yes, it is. You're not going to feel as weightless because you have more water. There's more surface area.
No, I'm saying if you do not have air in your lungs,
Then
what
I
happens?
sink.
Then you sink. So I'm saying if you were attached to that weight and you were hanging on that hook, I want to know how much you weigh. Because it wouldn't be 160 pounds or 180 pounds or whatever you weigh. It would be like 20.
If I'm submerged but not sinking or floating,
You would be sinking.
Yeah.
well, so I'm sinking but I'm not yet at the bottom.
Because you're hanging on to, look,
Okay, well then my
It's
weight
like-
is greater than 0 newtons.
no crap.
I can't get any more specific than that unless we have actual density.
You can search on the internet.
That's what he was on the internet. I was assuming he was doing that.
It said the density of the human body can go from just below that of water to just above that of water.
Okay, then let's Google the volume of a 210 pound, 6'4" male.
Because your average, yeah.
I bet our volume is.
Your volume
Yeah,
probably thousands.
Thousands.
Cube.
The human body has a density close to that of water, 1,000 kilograms per cubic meter. An average person weighs maybe 70 kilograms, which gives an approximate body volume of 0.7 meters.
0.7 meters cubed.
Yeah.
Sue, you use
Do
0.6
you see why that's a dumb question, Mr. Ernst? What is our volume?
because
Do I
why?
have to use density?
Because of our density of that of water, all you do is take your mass and divide it by 1,000.
Why?
Wait.
It's saying that our density is pretty close to that of water, which makes sense because about 70% of our body is made up of water. Fat floats, bones sink, muscle sinks. So 70% is water, the rest is bones. Muscles mainly water, fat essentially is oil and water. So in the end, our density is very close to that of water, which is why you're basically like a submarine. You hold your breath. Submarine too, you know?
No.
Submarine. Here you go, submarine. If you hold your breath, you're going to float. If you blow the bubbles out, you're going to sink.
Okay.
Submarines too. China have submarines. I don't know. Korea, or Thailand have submarines. Yeah. Periscope, you know. Go up, down. It's a ship, but it can go under the water.
Oh,
You know. You have them?
yeah, physics problem about that stuff.
Physics problem. Well, we're about to get to them. Get excited.
I'm not good at that.
Oh well.
All the volume force.
So, were you making a point here, or?
No, I was anticipating that we would weigh at least something. But it is tough for us to calculate.
Well, that's what I'm saying. I mean, it's going to be darn close to 0,
Yeah.
even if you are sinking.
Does that make sense? And that's why earlier in the year, when we were talking about astronauts at one time,
I would like to talk about them right now, if that's okay.
that one time we were talking about astronauts, they use water to simulate weightlessness because it's nearly weightless. So our buoyant force in water is nearly that of our gravitational force in air. Now, before Mr. Gottschalk talks about astronauts, unless it very much relates to the specifics that we were just doing, I'd like to finish helping them with the homework. Is that cool?
That's fine.
Okay. Alright, so did we get number 1?
Yes.
Excellent.
We did it yesterday.
Oh,
And Sue helped us.
Kyra, what's up? Need that sheet? No, you have that sheet. I need that sheet. Oh, I see. Okay. Come back in like half hour. Yeah.
My shit is in your office.
I know. Alright, so number 2. What do we got?
2.8 kilograms. Rectangular air mattress. Is 2 meters long and half a meter wide. And 0.1 meters thick. What mass can it support in a long forcing?
Air mattress. What's the volume of it, Arsenio Jamal?
0.1.
What? How thick is it?
0.1 meters thick.
How long?
2 meters.
How wide?
0.5
Good. 0.1 what?
meters cubed.
Okay. What else do they tell us?
2 kilograms.
2.0?
0.8, I mean.
Yeah, 8 and 0 look a lot alike. The 8's more like a snowman, and the 0 is just like a fold. So you'll get it soon, one of these days. Alright. So we have both its volume and its mass. It wants to know how much it can support in water. Okay? So basically what we're saying is buoyant force must equal gravitational force. Would you say that's a good place to start?
Yeah.
But gravitational force, not just of the mattress. The mattress's mass is going to come into play, as is Sue's and Mixer, whoever's jumping on, maybe both. You know? Ride the raft, and you ever been whitewater rafting?
Maybe not.
Yeah, for us, maybe not. Which of these can we do right from the get-go? Yeah. What is F of G equal to? Yeah, mass times gravity. How about buoyant force?
Density of water
Density of water
times
times the volume of the mattress times gravity. This is, remember, the definition of buoyant force. Volume time, it's the buoyant force in itself in a six word statement.
Oh. Weight of the displaced.
5 word statement. Yeah, weight of the displaced fluid. I don't like liquid, Sue. Why don't I like liquid?
Because fluid included liquid and
Air. Any gas is also going to have buoyant force. Okay, so weight of the displaced fluid. So that's how we find the weight of the displaced fluid. All right, so this, we're money. You know? This is what we need to know. Okay, so what do we have here? What's the density of water? 1,000 meters cubed.
Meters cubed?
Yep.
1,000 kilograms per meters cubed.
What's the volume of the mattress?
0.1 meters cubed.
What's gravity?
9.
We don't care.
Yeah.
Does it want to know the mass or the weight of how much that we can put on?
Wants to know.
What mass can it support?
What mass can it support? So I'm going to neglect gravity in both cases. Okay? I'm going to cancel them. And this has to be equal to what mass do we have? We don't know.
Yeah.
Yes, we do part of it.
Yeah.
What is part of it? 2.8
plus
plus AJ minus J. That's one variable. That's all your fat butts combined. They're going to sit on top of the mattress, and we'll see if we can support all of them. Plus, you follow what I'm talking about here? Because we already have used some mass. Part of the void force of the mattress is supporting the mattress. So crunch numbers, that's a piece of cake. What's 1,000 times 0.1? 100 equals 2.8 plus m minus 2.8. How much can it support?
97.2.
97.2. Sue, can it hold you?
Yes.
Yes! Can it hold two of you? I don't think.
Can hold you.
Can it hold me? Ooh.
Be close.
It would be very close. I don't think it can hold me. How much?
Hey, you're not that nice.
Mr. Ernst is fat.
Wait.
I don't know. It's close. I'm close to 100. Yeah. Close to 100 kilograms.
You're about 210 pounds?
Yeah. I'm like 97.
95.
95. It holds me. Money. I'm floating down the river.
Just don't eat a big meal first.
Alright. Good? 3.
Ferry boat is 4 meters wide.
Ferry boat.
6 meters long.
I can take it
So it's like a floating box. 4 meters wide, 6 meters long. It's the mattress.
Yep. Ferry boat. Go ahead. What else about it?
4 meters wide, 6 meters long.
When a truck pulls onto it, something happens. So it's not a shore apparently.
When the truck pulls onto it, the boat sinks 4 centimeters in the water. What is the combined weight of the truck and the ferry?
Alright, it's 4 meters wide, 6 meters long.
Which gives it a volume of.
How deep is it?
I think it's what? So
Ferry.
doesn't say.
Doesn't matter.
It doesn't matter.
Why doesn't it matter, Sue?
Because we just need to know.
How much it sinks.
Yeah.
It's all relative. We just know that after the truck pulls on, it's 4 centimeters lower than it was before.
Does that make sense? It's going to sink down.
A little bit.
So the thing is going to sink. This thing could be 100 meters deep. The fact of the matter is it sinks a little bit. Well, how much water is going to get displaced?
4 centimeters times 6 by 4.
You know, if this is the water, and this is what it used to look like, and this is what it looks like afterwards. What am I illustrating? It dropped down by how many meters?
0.4. Oh.
0.04 meters. Well, how much water got displaced? Exactly the same amount as
This.
the volume of this mattress from here to here. Okay? This moved down exactly that.
And now remember Archimedes' principle, and that the thing is still floating. So what does that mean about the volume of the water displaced? So what else can we say about that water?
Volume force equals the.
What does Archimedes' principle say? Look it up if you have to.
Volume force equals the gravity.
Magnitude of wind force equals the rate of distance.
Is that true?
Yeah, I'm gonna try to say Archimedes was wrong.
Ooh, I concur. Was this big?
Okay.
Big discovery.
Big discovery. We talked about this the other day. Was this big? Yes, it was. It was big for pirates. Right, Mick? Sue? You know what a pirate is? Pirates of the Caribbean. They float around and steal things. How is it big for pirates?
Because then they can literally float around and steal.
No, yes, because the pirates could then build their boats out of no more wood, and then the next time they got in a firefight, the fire wouldn't affect their steel boats, and their other pirate friends would be like, "Oh my gosh, steel doesn't float, it sinks. They must be God. Oh, we're gonna run."
That's history.
Good explanation.
That's
Alright.
wonderful, yeah. We'll
Anyways.
the pirates probably have access to a steel shipyard.
Come on. Same thing. We're just crunching three numbers: volume times
Density.
density of.
Water.
What's the density of water, Mick?
1,000.
1,000 what?
9 kilogram meters cubed.
That's
Kilograms per
interesting.
meters cubed, yeah. You know what that means? Kilograms per meters cubed? That means that in this cubic meter right here, this blue box on the floor up to about a meter high, in this-
1,000 kilograms.
yeah, if that were filled with water, that would weigh, would that have a mass of 1,000 kilograms? It would weigh 9,800 newtons.
I like to figure this out here because what is a kilogram?
1,000 grams.
Yeah, it's 1,000 grams, right? What is a meter cubed? What's a meter? It's 100 centimeters, right? So 100 centimeters cubed. You follow? Okay. What's 1,000 times 1,000?
Million.
It's 1,000,000, right? Okay. What's 100 cubed?
A million.
It's 1,000,000. Interesting. What's the units on the top? No.
10 grams
What?
per
Grams. Because 1,000 times 1,000, that was grams. What's the unit on the bottom?
centimeters.
Centimeters cubed.
Oh, interesting.
1 gram per centimeter cubed is the density. What is density?
Kilograms or meters.
What is density?
Oh, mass over.
Mass over volume. What? The first week of physics, we went through SI. What is SI?
International.
System International. It's this Chinese organization now. It's a French organization that, right? No, now it's a worldwide organization based in France. What is a gram? What's the SI unit for mass? Kilogram. Well, what, you guys remember what it was? A kilogram? Remember what it was? Like a, remember
It's an actual object that was a kilogram.
yeah, a meter was a, what was a meter? No, a meter is the,
Speed, it's distance
Yeah.
light travels in some.
no, I'm talking about back in the day. You know a foot? The English foot?
King's foot.
Foot, king's foot. The problem was it changed all the time. Remember this big conversation we had to talk about? What was the basis of weight, of mass before? Flip back, page.
It's like page 15.
Yeah, it's like page.
Metal, wasn't it?
What?
The metal.
A hunk of metal now.
Oh,
Wait, I thought that was it.
No, that was conversion.
Oh,
Go back.
yeah. Flip, page
Page 11.
11.
Oh.
Oh. Come on. Mick. Oh, now you speak and you say what you were owing about.
Mass of 0.001 cubic meters of water.
Mass of 0.001 kilometer
1/1000th of a meter, of a cubic meter.
cubic meters of water. 1/1000th cubic meters of water is a gram. Okay? Or, I'm sorry, is a kilogram. So if we had this cubic meter and we had it full of water, how much would it weigh?
What?
We've discussed this.
1,000.
No. How much
What's
would it
what's
weigh?
the bottom?
Sue, you see the blue?
Yeah.
This tall, 1 meter tall, box, glass, water. How much does it weigh?
7 kilograms.
How much does it weigh?
Oh, wait.
You don't need a calculator. You
No,
just it's 1,000. 1,000?
981.
9,810 pounds. That's why fish tanks suck to lift if they're full.
Pounds?
Pounds. 9,810
I'm
pounds.
talking about this.
What?
That can't be.
9.81 times 1,000.
1,000 kilograms times 9.81 kilograms per meters per second.
Yeah?
Square.
Yeah?
Is that heavy, Sue?
9,810 newtons divided by 4.48.
That will.
2,000 roughly, AJ? You're good college. That was it.
2,205.
How much?
2,205.
2,205 pounds this fish tank would weigh. Water is heavy. You guys know how much water weighs? Well, you probably don't know how much it weighs.
It's approximately
8.5 pounds to the gallon.
Yep.
Yeah, about 8.5 pounds for every gallon.
that. There's not quite a gallon. It's not totally full, but
Yeah.
that's.
This is probably 7.5 pounds. Full, almost 9 pounds to the
So
gallon.
think about it. If I stack that whole meter cube with gallons of water, that's a lot times 8.5 pounds, right? Plus, there's all that empty space between that I have to fill with water.
That's why you can, if someone ever bets you, I bet you can't lose 5 pounds in a day. You say, oh, give me a break. Just don't drink anything. You'll lose 5 pounds. Go run a mile. It would suck. You'd be thirsty. But you could easily lose 5 pounds. Water weight is pretty easy to get rid of. You could probably lose 15 if push came to shove. Wrestlers, high school wrestlers, to make weight. In wrestling, you have classes. And so the high school wrestlers, that middle of summer, it's 85 degrees, they throw on a sweatsuit and they go run. Big sweatshirt with a hoodie, sweatpants, big socks, gloves, the whole 9 yards. They take it off and the thing is drenched. And people are looking at it like, you're an idiot. What are you doing? It's 85 degrees and you're in a sweatsuit. But they, lose a bunch of weight because they're sweating.
So I have a question. Why don't we use this original standard anymore? Why isn't it still just 1,000th of a cubic meter of water per kilogram? Why do we have to now have the mass of a specific platinum iridium alloy cylinder?
We talked about this as well, if memory serves me correct.
We did.
Why did we change it, Sue?
What's wrong with...
Look to the left, bottom left. That's the new kilogram. Very fancy. Looks like a blue spool.
What's
iridium alloy? No one?
Because
Water
is not pure.
Good. Water is not pure.
Therefore, yeah.
What?
Well, go ahead and elaborate upon that.
The platinum iridium alloy cylinder is pure. I don't know.
Thanks, AJ.
Why is water not pure?
AJ, how are your teeth?
What do you think the original...
How are your teeth?
I don't know.
I mean, decent. You got a lot of cavities?
Yeah, I got one.
Dude, just one. That's not a lot. Mr. Gottschalk, you got
I have
cavities?
several, yeah.
He has
I mean,
more
I've
than...
had them filled.
He
I
has,
still
he
have
has
them.
more than one. Yeah, I don't have any like that. He has more than one. You got cavities? Sue? In China, they put anything in the water for your teeth?
Lead.
They put anything in the water for your teeth.
Here in America, they put something in the water that's good for your teeth.
Fluoride.
Oh,
They put fluoride in the water here in America for your teeth.
They used to, yeah.
I'm not fixed.
Water
What's
also
that?
has minerals and things dissolved in it from the
Yeah.
ground. What kind of water do you think they used for this original standard?
boiling water.
Or in France? What'd you say?
Disgusting French water.
I would guess probably some sort of lake water, maybe rainwater, right? Something like that.
Water.
Rainwater is the dirtiest.
French water is?
Rainwater.
Rainwater?
acid rain.
I heard Chinese water is dirty.
Well, plus there's a bunch of think about the time period here too. There's
Because
probably a
of
bunch
the-
of bacteria swimming around the water too. More weight.
Atmosphere is nasty.
But so what if they had used seawater instead to measure that kilogram?
Be heavier.
Would
Yeah.
the kilogram be heavier or would the kilogram be lighter?
Heavier.
Heavier.
Yeah, there's more mass in the water, right? Because of
Salt.
salt.
Even pure H2O can have different densities.
What
This
if
is real big last year at the Fukushima thing? Anyone know what they use to cool the nuclear reactors at power plants? What kind of water do they use? They don't just use H2O. Call it something. What? What are you laughing at?
I don't know.
That's awesome. What are you laughing at? I don't know.
I'm laughing why I don't know what you're talking about.
The disaster, the natural disaster with the nuclear power plant last year
In Japan, the tsunami?
remember? They had to cool it with seawater because they ran out of, well, not ran out, but it destroyed the cooling mechanism, isn't that right?
Yeah. They couldn't pump the good water in there because it got contaminated. The lines got ruptured, and so they dissipated all this water they had spent a long time collecting. They collected a certain type of water. It's in a closed system, so they don't lose it. It's special water. Why is it so special?
It's heavy water.
It's heavy water. What the heck does that mean?
Heavy water. You guys talk about heavy water in chemistry last year?
Has more
Did you talk about heavy water in chemistry?
the bottom number.
More than bottom number.
Yeah, I think I know what you're getting at, Sue. Alright, atomic numbers. Anyone know how many protons oxygen has? Henry can tell you.
I know.
8.
8.
Good.
Come on, AJ, you look like who? You just passed chemistry. You should know 1 through 10.
Alright. Assuming that this is not an isotope, how many neutrons does the oxygen have?
Depends.
How many electrons does it have?
Well, that part is yeah.
Assuming it's not a charged,
No,
or
it's not an ion.
It's not an ion, right?
I mean, in water, it can become ion.
ion.
It shares bonds, it shares with the hydrogen. But by itself, oxygen is this. Forget the electrons for now. 8 protons, 8 neutrons. What about hydrogen? How many protons, how many neutrons does
AJ
hydrogen
can
have?
answer this one.
More.
One proton, how many neutrons, AJ?
What?
How many neutrons does hydrogen have?
I don't know. 1,
No,
2.
no neutrons. Hydrogen is just a single proton. That's normal water. Heavy water is made of deuterium, which is a special form of hydrogen, which has a neutron attached to the proton.
Wait, hold on. I don't remember. Why does hydrogen have a proton and no neutrons?
Because it's light. I don't know. It's the lightest
There's
element.
another type of water, right?
It's the simplest one. Yeah,
Does helium have any neutrons?
yeah. Everything has neutrons except for hydrogen. Yeah.
It is not that left column, all of them, or
No, it's just hydrogen because it's one proton. It's close enough to 0 that it can get by without any. Everything else you have to have somewhere similar to the number of protons. Like carbon, you have carbon 12, carbon 14. Carbon has 6.
I don't remember talking much about that in chemistry. The fact I thought all protons and neutrons were the same unless they were isotopes
The water.
Protons and neutrons are the same. Oh, you mean
for a given element.
Great.
You
I
know?
don't think that's true when you get to the heavier ones, like the radioactive ones. Part of the reason they are unstable is because they have different numbers.
How 2 hydrogens each together? If it's like
What'd you say? One more time. What'd you say?
how 2 hydrogens like
2 hydrogens, right? Yeah. So we have a total here. Up here, we have a total of 10 protons and 8 neutrons, right? Because you have 2 hydrogens, each with 1 proton. Down here, these deuterium is heavy hydrogen. It's hydrogen with an extra electron, or I'm sorry, with an extra neutron. Well, now we have 1 plus 1 twice, plus the 8 in oxygen. So now you have 10 protons and 10 neutrons. Okay? So you have a total of 20 of those nucleonic particles. So this is 18.
No, they're all within about 1. Lithium has an extra neutron. So does beryllium.
Okay. Even the heavier ones are close?
Like no, once we get to the metals, they're messed up.
Right, yeah, that's what I was getting at. Most of the non-metals,
Page
like this
965. Some of the metals, but all the normal levels.
But the point is here, I have more mass basically packed into the same area. Okay? If I have one molecule of this is about the same size as a molecule of this. So you get a whole big reservoir of water. You have the same number of these as you would the number of these. In these though, they're each heavier, they're denser. Okay, the water is denser. So why do they use that to cool a nuclear reactor? Why do they want denser, heavy water? Why do they want that?
First off, what is a very unique and cool characteristic about water? And it kind of shows you that if this wasn't the case, the Earth's temperature would fluctuate incredibly. The surface temperature of the Earth would fluctuate a whole lot more than it does. Like right now, you know,
We're doing this a lot next chapter, but
yeah. But what is true about water?
It gets hot slower.
Yes, it's called a very high specific heat. God designed water with a very high specific heat. What does that mean for us? It means that even if we have, let's say we have a straight week in July of 100-degree temperature.
The temperature in the land will higher than in the water.
The temperature of the land will go up, but it's not like it's going to go up to 100 degrees, you know, where it's dissipating throughout the earth 10, 12 feet down, 100 degrees. There's a lot of water in soil. Obviously, there's a lot of water in the ocean. Those bodies of water and the water in the soil keep the Earth's surface temperature at a relatively similar manner. I don't know what would you say the average temperature of the Earth would be? The Earth's surface as a whole, probably 50.
yeah, about 50, 55 degrees somewhere.
You know, 50 or 55 degrees as a whole. And that is safe for us. Because if water specific heat were higher or lower, then in the summertime, you know, right now we already have issues if it gets to 100 degrees. Well, if it got to 100 degrees for a couple of straight weeks, I mean, we would have huge issues.
Because all the water will be evaporated. Specific heat is the amount of energy basically that it takes to heat some amount of water by 1 degree.
Mm-hmm.
Okay? The more, and water takes a whole lot of energy just to raise by 1 degree. That's why when you boil a pot of water to make your rice or your pasta or whatever, you gotta put that water on the stove for like 8 or 10 minutes before it even starts to boil.
Are you gonna learn that?
What's that?
Are you gonna learn that?
Yeah, next chapter we talk a lot. Next chapter is heat. Heat and temperature. So we'll talk a lot about that. But why do we base all this stuff on water? You know, why is specific heat the amount of energy it takes to raise 1 gram of water or 1 cc of water by 1 degree?
And why is it to a kilogram?
Yeah, why is density based upon water?
Density too.
Density based on water. Why is all this stuff based on water?
Because water is everywhere, right?
It's everywhere and it's vital for us, right?
Water is everywhere and everything. It's not in our solar system. The only planet that has life is Earth. The only planet that has water is Earth. Well,
the only planet that has water in the habitable zone, water that is in the temperature range distance from the sun where it can remain liquid.
So ice on Mars, but ice isn't water.
He's just going off on tangents to keep me from talking about astronauts.
No, this is good.
This is good, yeah. All right. So anyway, the denser it is, the heavy water has an even higher specific heat than regular water. Because there's more stuff in there, it takes even more heat to raise that water. Therefore, it's a more efficient cooler because it can take more heat. It can absorb more heat from the hot nuclear reactors. When that stuff all spilled out in the tsunami, they had to pump seawater in, which, yeah, it's probably better than this, but it's impure. And so that started things rusting, things like that, that have now permanently damaged the reactors there. But that's why they use heavy water. That's what heavy water is. The density of water is not always the same, and that's why they didn't keep using it for the standard. So are we still on number 3 or are we number 4?
We've been on number 3.
Good.
No, we're done with number 3. Are you kidding?
Yeah. It's you started talking about.
All you have to do is multiply the volume of that mattress times the density of water times gravity.
We want the mass, right? How much mass can it hold? Density of water is 1,000 kilograms
You're the
per
teacher.
cubic meter. Volume is 0.4 times 24. What's that? 119.6?
Did they give you?
0.04. Is that, am I way off here?
Yeah.
0.96.
0.96. What did I get? 1.96. All right.
Why would you just use raw?
Yeah, I don't know. I agree, Sue.
Why?
Why don't we just use rho VG?
Because.
That's fine too. Go for it.
You know?
That's fine. That's this. Okay. I'm just giving you this. If you want to play by gravity, you have the balloon.
Got it.
You know. That's
Oh, I see what you're saying.
Interesting.
Because in this
Yeah.
case, if it's floating, Archimedes' principle holds true. So equal. So how much weight can that?
9.42 times 10 to the third.
9.42 times 10 to the third, so 9,420 newtons. How many kilograms? Does that ask weight or mass?
No, that's for weight.
Wait, 9,420 newtons.
Kilograms, it's easy.
Was the truck.
96 kilograms.
Okay?
Yeah.
Beautiful.
So yeah, it must be a pretty light truck, right?
Ah, that's not too light. A couple of thousand pounds. That's about right.
960 kilograms, yeah. Okay. Okay, number 4.
9,600.
Huh?
9,600.
No, dude. What's 1,000 times 0.96?
That's mass.
960 kilograms.
Kilograms.
Yeah, that's what I said, kilograms. Which
Yeah.
is 9,000.
1,000 something newtons,
Yeah.
which is like 2,000 pounds, so it's not that light. I mean, for a truck it's light, but for a vehicle it's not that bad. I mean, your little,
Yeah, I guess I'm thinking truck plus ferry, you know.
yeah, your little Toyota probably weighs 2,000 pounds. Maybe not.
I don't have a
Maybe
Toyota.
1,500.
You're talking about, yeah, my road, yeah.
No.
Oh, my little Honda
1,500,
outside, yeah. I think
probably
it's like,
2,000 somewhere.
when I'm
My
driving
truck's
that
about
thing,
5,000. So,
that thing is blown around by the wind.
yeah.
Alright, number 4. What? Balloon is filled with helium at 0 degrees Celsius, 1 atmospheric pressure. What does that have to do with anything? What does that have to do with anything? Number 4, how do I do that one?
Volume for no baby.
Rho VG? Sure. Made it to the buoyant force. What's rho?
1.29. The density of air.
1.29 because that's the density of air. Right, okay.
Times
1.29 times
4/3 pi times
What is X here?
0.5 cube.
Yeah, there's just a bunch of extra work here. You gotta find the volume of a balloon with a radius. That's all. You gotta find the volume of the air. You gotta go find the density of the air. Once you find that, you find the buoyancy.
Slopes are going to be constant.
So what do you get?
Because
It didn't get anything.
Do you understand what we're just talking about here?
No.
Okay. Well, it asks for the force of buoyancy first of all, right? In part A. And then to the buoyant force acting the balloon. We got this balloon.
What's going to be the same? The rows are all the same. The axis.
I don't know what kind of balloon it is. We'll make it a basket type so there's people inside of it.
Like,
Alright, so
here.
nice pattern on it. So this balloon has a radius, we're going to assume it's circular or spherical, radius of 0.5 meters. That's what it says, right? 0.5 meters, that is not holding any people, that's just a balloon. Okay. 0.5 meters. Well, we need to find the volume of that spherical balloon agent. Okay, because I need volume, because force of buoyancy, rho times volume times gravity. You got that in the equation sheet, right? This one?
You just say that.
Okay. Density, we're talking about the buoyant force on the balloon, okay? Which means something outside the balloon is pushing it up. That's air, right? It's in air. That air has a density that's heavier than the balloon. Otherwise, the balloon wouldn't rise, right? So the density of air, we find in the chart 1.29. The volume of the sphere,
Because let's say it's
4/3 pi 0.5 cubed. Volume of the sphere
what's the
times gravity. So that's going to be part A.
what's the slope of sine 1, so it cannot be this one. What?
So what is the force of buoyancy there, AJ? Why'd you get it calculated?
Didn't check.
No. Yeah, you could. Y prime equal to what's cosine at, this would be dy over dx. So that means what is the, if you plug in 0, what's the slope? 0 is 1, just like the slope of sine.
There we go, good. So that's the buoyant force acting on the balloon, but we've missed one very important piece of information. Okay, I mean that is part A. You got part A. But why? What about the air inside the balloon? They gave us that density for a reason. Why? Why do we care about the density inside the balloon? That wasn't necessary.
Wait. We need that density for the mass.
What'd you say?
For the mass of the.
Right. It wasn't necessary to find buoyant force because buoyant force is just based on the volume of. Think of it as something submerged in water, AJ. The balloon is displacing air. Okay. For buoyant force, all we need is the amount of air it's displacing. We need the volume. What we need now to find the mass, what would the density? We have the volume.
For whatever function this is.
So now we find the mass. And to do that,
the slope is
well,
not 0.
then do net force. Well, net force is what? What's net force? What minus what? What forces?
FB
Plug in
minus
0. F0 for x.
Right.
Slope is 1 everywhere. So it's got
Buoyant force minus force of gravity. It's